Does anyone use the app called Flickster? Ever heard of it? A couple of you have. It's a movie going app. It's kind of cool. They show you, different movies, and you can find out, what's coming, etc., what's playing. But the thing I like about it, and the thing we're going at here, is that they show you a couple ratings. They show you what critics thought of the movie, and they show you what viewers thought of the movie. So you get two different sets of ratings. So the question is, how do these things compare? So just this morning, a little bit before class, I spent a little time and I pulled a bunch of movies off of this and plotted them. I plotted 2 points. I plotted what the movie critics thought, and I plotted what moviegoers thought. So what are your thoughts? What do you see when you're looking at this? Yeah, it's not a normal distribution. That's true. So this is a scatter plot of the data, and we'll do a scatter plot of some of our own data coming up. What's that? Yeah, there seems to be a little relationship between these, right? I mean, higher ratings by critics tend to be higher rated by the users. Oh, there's certainly some exceptions, right? I didn't take a note of all these, but boy, movie critics didn't like this one, but movie goers really did. So, to you, right, movie critics? We liked it. But what also catches my eye is that those that are both highly rated. I mean, if it's highly rated by one, it's going to tend to be highly rated by the other. Lower ratings, it's not as much of a tendency. But this is getting at what we're going to work on in this section, and that is, what's the linear relationship, or how much correlation is the word that Chris used, and he's spot on with that. How much correlation is there between these two things? So let's look back before we look forward in the following way, and that is with this little reminder of statistics and parameters. So this is section 10.2, and we should probably zoom out a little bit so you can see something other than my knuckle. All right, so mean, standard deviation, proportion, and correlation. Now for each of these, depending on whether or not you had a population or a sample, we could calculate all of them. It's just, what are you going to call it? Are you going to call it a statistic? Or are you going to call it a parameter? So your statistics, well, what's our symbol for the sample mean? X bar. Good. Someone else for the parameter. What's the parameter here? Mu. Thank you. Let's keep going. Other people. Standard deviation. S. Sigma. Good. Someone else now. Proportion. What's the sample statistic for proportion? P. Close. P hat. And then proportion, or the parameter, would just be P. It's just P. Now correlation is a little bit annoying. Correlation is R for the statistic, and I don't know who came up with this. Don't shoot the messenger. It's another Greek letter. It looks like a P, but it's actually a rho. So yeah, I didn't choose it. I probably would have tried to choose something that didn't look like a population parameter for proportion, but it's rho. R-H-O. So pretty soon you'll learn enough Greek letters to spell your name. Let's understand some stuff about R, the linear correlation coefficient. So let's go to our handout then. Some properties of R. R is going to be between 1 and -1. So let me make that part clear. Negative 1 is less than or equal to r is less than or equal to 1. That's going to be the same is going to be true with rho, of course, the parameter that it's trying to estimate. Now, if r is greater than 0, then increasing something on the x-axis tends to increase something on the y-axis, and vice versa. If r is less than 0, an increase in x causes a decrease in y. Now, when you have r equal 1, you've got a perfect linear relationship. Same thing with r equal negative 1. It's just in this case, as one increases, the other one decreases. But it's still a perfect linear relationship. Now, as your data spreads out from some theoretical line, that linear relationship deteriorates a little bit. So you can see that here r is negative 1. Here r is not quite negative 1. It's not a bad relationship. I mean, certainly this is very suggestive. If you saw some data like this, you'd say, oh, there's something going on there. Now, how about down here at 0.08? What's this look like? Yeah, looks like something you see in a psychologist's office, right? So tell me what this picture means. So, yeah, it looks like a blob. Doesn't look like there's much going there because r is pretty close to 0. There's no real linear correlation. I mean, sometimes you get something a little bit different than 0, but it doesn't really mean much. On the flip side of things, we could have a nice, perfect, positive linear relationship. Here, you still have a good positive linear relationship. It's not quite as strong, but it's still pretty strong. How come this last one is 0? I mean, there's a nice relationship here, right? Perfect. It's not linear. What r represents is the strength of the linear relationship. And though there is a relationship here, it is not linear. That's why you're getting an r equals 0 here. It's not a linear relationship. Okay. So what we're going to test is whether or not our value of r represents something statistically significantly different than 0. So we're going to be doing hypothesis tests of rho equals 0 versus rho different than 0. So this would say that there's no correlation, and this would say there is a correlation. And that correlation would be linear. You should try and get familiar with this term right now, linear correlation coefficient. There's a term that's coming up in section 10.3 that'll be easy to confuse with this one. Okay. Let's take a look at problem number 11 here. And I just want to emphasize a little something about the linear correlation coefficient, and that is it's sensitive to outlying values. Now, in this one here, you can kind of think that, yeah, that looks like a pretty nice linear relationship. And, I wouldn't fault you for saying so. But the strength of this linear relationship really depends heavily on this one value. if we zoom in considerably, if we were just able to throw out that one value, if we decided, you know what, that was an error in measurement or something like that. If we calculated R here, what do you think I'd get? What kind of value of R would I get for just those 9 points? 0. Yeah, there's no linear relationship. Close to 1 would be a perfect linear relationship. Here, there's nothing. It just looks random. And that randomness would be reflected in a value of R for R equals 0. But this one out here gives it a lot of influence. Now, the nice thing about your stat packages is that they'll help you measure, what are influential values. But this one, yeah, has an awful lot of influence on our final conclusion. Let's take a look at problem number 20. Okay, so table below lists weights, carats, and prices in dollars of randomly selected diamonds. All the diamonds are round with ratings of very good cut. They all have color rating of F, slight color and clarity. VSI, very slightly included. The values based on data from retailer Blue Nile. For diamonds of type described, is there sufficient evidence to conclude that there's a linear correlation between the weights and the prices? Do these results apply to other types of diamonds, such as those with different color and clarity ratings? All right, so basically, I think there's 4 C's of buying diamonds. So color, cut, clarity, and carat weight. So guys, remember that when you go shopping, all right? And the big one is carat, which is how much that thing weighs. Diamonds, unfortunately, are a very, very concentrated form of your money. So let's see if there's some kind of a linear relationship here. So what we're going to do is we're going to plot these values. We're going to plug them into StatDisk. So we'll go over to StatDisk. Let's clear out some data. I don't have anything here. And then enter in our weights. So the weights would be 0.3, 0.4, 0.5, 0.5 again, 1, and 0.7. Now it seems to be, at least in my experience, that 1 is kind of like this magic number. That is, boy, if you're under the 1, then it doesn't have as much thrill. But if you can say to somebody, yeah, it's a 1 carat diamond, not a 0.9 or a 0.98, it's worth a lot more all of a sudden. Let's see if that's borne out by the data. So $510, 1,151, 1,343, 1410, 5,669. Don't want to say I told you so. Someone say it for me. All right. Now, let's first start by looking at this thing, just plotting it. And what we'll do is we'll do a scatter plot of the data. So there's scatter plots. I think that's underneath data. So if you go underneath data and scatter plot, then it's going to ask you, well, what do you want? So X values is going to be our weight. Y values in column 2, that's going to be the price. And then you can plot it. So there you go. You can see that all by itself, way out here at 1, you've got this one lot, you've got this 1 point, and it's above this imaginary line that it's been drawn for us. Overall, does it look like there's some kind of a linear relationship between these two? Price and carat weight? Yeah. Is it going to be a positive or negative value for R? Positive, yeah. The more it weighs, the more you pay. Pretty simple. So let's test whether or not there is such a relationship if it's significantly different than 0. Now, if it's 0, then to represent your data, you just draw a horizontal line. That's all you're going to draw, as opposed to a line that has a slope. So for problem 20, test H naught such that rho equals 0 versus rho is different than 0. Okay. Let's go back to StatDisk. We'll make our test at, say, the 5% significance level. That seems to be pretty standard. It's not like if we get this thing wrong that there's an earth-shattering consequence of this. So 5% seems like a reasonable standard. I can close this out. I'm going to go back to StatDisk, analysis. This time, underneath analysis, you should see correlation and regression. We're going to get more information from this than we really need right now, and more information than we can really understand. But at the 5% significance level, correlate the x variable with the y variable. Let's evaluate. And we get a p-value of 0.00155. Okay. Alicia, what's that telling me we should do with our null hypothesis? Good. Reject H naught. Yeah. Clearly there's a nice relationship going on here, and it's significantly different than 0. So looking back at the original problem, is there enough evidence, sufficient evidence to conclude that there's a linear correlation between weights and prices? So if there's a linear correlation, is our original claim that we're testing, is that HO or HA? Where do you think this one falls? Yeah, this is HA. So sufficient evidence to conclude there is a linear correlation. That's HA. So let's take a look at how we're going to word this then. Our original claim does not contain the differential condition of equality, and we rejected it. So the sample data support the claim that there is a linear relationship between weight and price of diamonds. Sample data support the claim that there is a linear relationship between the weight of a diamond and its price. All right, are we okay with problem number 20? Okay. Okay. Charles?
Quick question. In each of these problems, should we look at the plot?
It's a good idea to look at the plot to make sure that what you see matches the results you get. I mean, sometimes I see kind of a big disconnect.
The
That
plot will give us the answer.
Yeah, depending on what you click on from StatDisk, yeah. I mean, one of the things you can get from the correlation regression submenu is the scatter plot. So there you go. There's your scatter plot. You look at that and say, yeah, that looks like there's some kind of relationship there. And then you can go back here and take a look at some more stuff. In fact, they give you some stuff that we'll cover more in section 10.3. But really what they give you is the equation of the line that predicts that. So something like this. Now what this is saying to me is that the slope is such that it costs about $7,000 a carat. That's what this is actually saying. Of course, there's a huge negative value for the y-intercept. So, you know, once you get to the first carat, it's going to be around $5,000. So, yeah, zero. Well, yeah. So what this is saying though is that you have to be careful about making predictions outside of your data because you're exactly right. According to the equation that we just had, then you'd have, you know, they'd have to give you a rebate to buy a 0 carat diamond. You walk up and say, hey, where's my 0 carat diamond, man? and pocket $2,000. So that's a difficulty when you're making predictions. Particularly, and this happens a lot, you want to make predictions into the future. It's like, okay, this is what's happened in the past. Where's it going to go in the future? Depending how far away you go from your data, you run into a lot more uncertainty. So, nice observation. Okay. Anything else on this one? Have you ever seen that phenomenon that, you know, a truck passes you by and the sound is whining really, really high pitched, and then as it passes you, it's really, really low pitched, etc.? It's called the Doppler shift, Doppler effect. And what's happening is that as something's moving towards you, the sound waves are being compressed, and as it's leaving you, sound waves are being stretched. Now, I'm not going to try and give you a complete physics lesson here, but light travels in waves. Light's part of the electromagnetic spectrum. And when you look out at the night sky, what you can see when you look at starlights is that some of that starlight has been shifted. It has the same Doppler effect that sound waves do. So it's been red shifted, means it's moving away from us. It's been blue shifted if it's moving towards us. And in the 1920s, Edwin Hubble noticed that there was an awful lot of stars that were moving away from us. And in fact, they're moving away from, the farther they are away from us, the faster they're moving away from us. So there's kind of an interesting relationship here. In fact, the universe is expanding. It's kind of tough to believe. So here's a picture taken on the night sky and a little sampling here. And what you can see is that most of these objects that are highlighted here are actually being red shifted, meaning they're moving away from us. So let's take a closer look at this in the form of problem number 19. I think I have that one graphed for you. Charles was asking, should we plot the data originally? Yeah, absolutely. In fact, I already have this one plotted. If you had to guess, well, first of all, does it look like there's a linear relationship here? Yeah. If you had to guess at the value of R here, what would it be? 1. That looks perfect. Now, I don't know if the author cherry-picked the data to get something like this or not, but let's try this one in StatDisk and see if we can reject or accept a claim about a linear relationship between the redshift of distances of galaxies and clusters. So let's clear out this data here. Yes, I do want to clear it. Now, the one thing that I would criticize is that they don't exactly give the units of redshift, but typically there's something pretty bizarre like kilometers per megaparsec or something like that, and it's kind of confusing. So maybe it's just as well. 0.233, 0.539, 0.718, 0.395, 0.438, 0.0103. So those are the red shifts. Now I'll put in the distances as well. And these the distances they do give these the units. These are billions of light years. So a distance of 0.32 or 0.75 in this case. 0.75, that'd be 0.75 light years. 0.75 billion light years, which is an awful long ways from home. Magic value of 1. 0.55, 0.61, and 0.14. So with all our values, let's again plot these, this time in StatDisk. So to plot these, we'll go to Data and take a look at the scatter. You know what? Let's just cut to the chase. Let's go to Correlation and Regression. Correlate these two, 1 and 2. Let's click Evaluate, and we'll click Scatterplot then. Boy, that's looking pretty perfect. In a lot of social sciences, it's tough to get R values this high. In the social sciences, you're going to be happy with R values that are a lot less than this. In the physical sciences, yeah, they're going to tend to be closer to 1. I can't really speak for my colleagues in the sociology department as to what a good R value is, but it's tough to explain human behavior. It's much more easy to explain things in physics. Okay, so let's set up an alternative hypothesis here. The question is, is there evidence to conclude that there's a linear correlation between the amounts of redshift and distances to clusters of galaxies? So, problem number 19. H0 and HA. So pretty much the same thing as before. Rho equals 0 and rho is not equal to 0. Just make this look more like a rho and less like a P. There we go. So there's a nice way to fix that. There we go. Rho equals 0 and rho is not equal to 0. No, it's actually an A. Really. It's there. All right. What should we use for alpha? They don't suggest any value for alpha, so what do you think? 0.05? I'm gonna go wild here. We're gonna go 0.01. I'm pretty sure that we'll be able to reject. I'm pretty confident that we're going to get a p-value that's going to be really, really infinitesimally small. So let's take a look at that. Going back here, I'll put aside my scatter plot. And this is already the output for my correlation. So let's see, critical value of R. Wow. This is our sample test statistic. We're getting a value of R equal to 0.9999921. Man, that's about as close to 1 as you can get from a set of data. Correspondingly, we got a p-value of 0 to the nearest thousandth. P is 0.000. David, what's that saying about our data here? Yeah, reject H naught. Absolutely, that's not even close. And it matches what we expected based on our scatter plot. That scatter plot looked perfect. So, last but not least, let's put our expressions into words. The sample data support the claim that there is a linear relationship between redshift and distance. Okay. We're looking good on that one. Problem number 19 there, one of your homework problems. So this is kind of a lead into stuff that we're going to be doing more of on Wednesday. And that is correlation versus causation. What we're testing is, are these results correlated? But sometimes there's a tendency to think that there's a causal relationship between them. Sometimes there is, sometimes there isn't. One might cause the other, one might not. It just depends on, a particular case. One case that the author cited was the price of pizza in New York and Subway prices. I'm not talking Subway, the restaurant change. Subway prices. And you'll find strange correlations like this, but they seem to march together in lockstep. So, they're correlated, but is there a causal connection? Can I say that one causes the other? No. It's just a correlation. All right? One does not cause the other. We discussed this one earlier this semester. Body weight and how much you watch TV. There's a nice correlation between these two. But is it a causal relationship? What causes you to gain weight is not burning enough calories, taking in more calories than you need. And if you're spending a lot of time watching TV, it's tough to burn all those calories. But it's a correlation. It's not a causation. Smoking and your chance of getting lung cancer. How much you smoke, your chance of getting lung cancer. Is there a causal relationship, or is there just a correlation there? Well, I think they've pretty well established, at least in my mind, that smoking causes cancer. One of the things that happens is that I think some of the active, or some of the 4,000 chemicals that are in cigarette smoke bind with radioactive radon in the air. And when you suck it down into your lungs, and you can suck it down really deep because they all come with menthol to help you get over your cough, then, well, but there is physical evidence. They've done genetic studies that show what's,
It separates your DNA when you take those chemicals, and it's likely that they're going to reattach in a different way, and that'll be a mutation.
yeah, which is your cancer. So I would say that that's causation, but there's a percentage of Americans that don't believe in this link. Hey, and that's their right. How about as you're driving down, say I-75, and you pass Oakland Mall, and you see a highway sign, or you see a sign for the Oakland Mall, and one of the things you see there is the temperature, and the temperature on a highway sign and the temperature on your car's thermometer. Yeah, thermometer. Yeah. Are they going to be correlated, or is there a causal relationship? I think correlated. Temperature here doesn't cause your car to read anything, but they are still measuring the same thing, so they are going to be correlated. How about the one we did earlier with the ratings of movie critics and the ratings of moviegoers? There's a nice correlation here, but is it a causation? Does what a movie critic says about a movie, does that cause you to like or dislike a movie? Typically, no. No. So, again, it's a correlation versus a causation. And certainly one of the things that I'd like you to know is the difference between those two. We're going to go over more of that, again, in two situations. We'll do some more of it in the linear case. We'll also talk about it when we start talking about contingency tables in Chapter 11. Okay, are you comfortable with what I expect from section 10.2? Should be able to calculate and interpret correlation and know the difference between correlation and causation. Okay, so for homework, try problems 5 through 21. You can skip 19 if you like, although at this point I hope 19 is pretty easy.